Okay, now let us continue the analysis of this 555 timer for certain applications. So let me configure this as a stable multi-vibrator, a stable multi-vibrator. So let us try to understand what is this a stable multi-vibrator is. So we know that this is a multi-vibrator. So vibrator is nothing but which operates between two states. So let us assume state 0 and state 1 here. So this is vibrating from 0 to 1 state and 1 to 0 state, and it is keep repeating. Of course, this is what is the vibration means. So when I say state 0, it is 0 volt or minus VCC. When I say state 1, it is plus VCC or 5 volt, 15 volts, whatever the volt is. So it's like a 0 volt and 5 volt, a typical vibrations will be. So now when it is said astable, so this state of 0 is not stable for a long time, and if it is there in state 0, it is there for a certain time, it will go to state 1, and even this state 1, it is not stable, so it is keep changing its state from 0 to 1, 1 to 0. That is happening repeatedly, that's happening repeatedly. So this time, suppose if you call it as T on, this T on is repeating for the same time after the T off. So this T off and T on are repetitive. So if it is 2 millisecond, this is also 2 millisecond. If it is 4 millisecond, the T on is here also 4 millisecond. So this is like a periodic signal of 0 and 1, which we can call it as a square wave of certain frequency and duty cycle. So since this is the state is not state of 0 or state of 1 is not stable, it is called as a stable multi-vibrator. So let us try to configure this 555 timer as a stable multi-vibrator. So let us, of course, as we saw in the previous video, let us identify the pin numbers of this. This is pin number 3 output, pin number 1 ground, pin number 4 is reset here, pin number 8 is VCC, pin number 7 is discharge pin. You can see this is discharging to ground through this transistor, and this is pin number 6 threshold voltage, pin number 5 is control, and pin number 2 is trigger signal. So we have, so as we saw in the previous video, so we have 8 pin DIP, which is nothing but 8 pins configured on either side of so we have these 8 pins of the 555 timer. Pin number 1, 2, 3, 4, 5, 6, 7, 8. This is 555 pin number IC, which is in the market available as LM555. So this is ground pin number. Pin number 2 is trigger. Pin number 3 is output, and pin number 4 is reset pin, and pin number 5 is control voltage. Pin number 6 is threshold. Pin number 7 is discharge, and pin number 8 is VCC. So this is the pin numbers. So let us now do the connections for configuring the stable multi-vibrator. Let me short this VCC and reset. So I don't want to reset. That's why I'm disabling the reset pin by connecting it to VCC. So this is VCC now, and let me have, of course, let me short this pin number 6 and 2. This is my shorted point, and let me extend this pin number 7 here. So between pin number shorting of 8 and 4, that is from VCC, you connect a resistor by name R12, discharge, and there is a resistor connected from pin number 7 to the junction of 6 and 2. Let me call it as R2, and there is a capacitor now connected from that junction to ground. So this is CT, and let me also connect a capacitor between 5 and ground, which is for stabilizing the voltage at pin number 5, which is two-third of VCC, This is what we have. So now, of course, let me ground this. So this is the connection what we have. So we have actually uh, two resistors and a capacitor, and of course there is one more capacitor connected here. Suppose if I want to write the circuit in terms of IC, I can write this as, this is my IC. Suppose if you write this is your IC, and if you just configure it like this, so this is this, connect this, your output point, this is grounded, and this is your capacitor. So this is connected to VCC. This is pin number 8, 4, 7, 6, 2, pin number 1, pin number 5, pin number 3. This is 555 time. This is the actual circuit that you'll be connecting. So this is R1, R2, CT, which is exactly the same thing here, Of course, this is whatever that is green written is within. It is internal to the IC. The external connection are these R1, R2, CT, and this you can call it as CS, stabilizing capacitor. And this is my output point. Let us see its operation now. So maybe you can assume let the capacitor voltage of this is initially 0. So now let me consider the capacitor voltage is now as 0. Since it is 0, so if you can see here, when this capacitor voltage is 0, you can see that 0 is going here. So is this now 0 here? Is this now also, can see the same 0 goes here, 0 volt goes here. And how much the voltage you have? The voltage that you have here is 1 by 3 VCC. This is 2 by 3 VCC, 2 by 3 VCC. So these are the voltages at the inputs of your comparator. Since it is 0 and this is 1/3 VCC, so V plus is more than V minus. So now since V plus is greater than V minus, so what you're going to have? So you will going to have this as, this is now when V plus is more than V minus, you have it as 1 here. And since this is there, since okay, now you have 2/3 VCC, that is now 0, which is more now, it is this is more, so this is 0, correct? So it is now set, when it is set, you have this output as 1, this output as 0, when it is 0, so this is now off, because there is no base drive for this is off. So this is off means, so you cannot discharge through this, the current cannot flow through this, meaning when the capacitor voltage is 0, you have it as 0 and this is 1, meaning I'm just assuming that. So let me have a switch here. As long as this switch is closed, as long as this switch is closed, output is at high. As long as this switch is closed, the capacitor voltage is 0. When it is 0, here also it is 0, this is 0, this is 1, the output voltage is always high. So if your VC is 0, then your V0 is at VCC. Correct? So now what I'll do, I will open this. So I will open this means this will now, whenever I open this, the capacitor starts charging to this. Capacitor start charging to this. Now at the time, some time, so I just opened this switch. Now the capacitor started charging. The capacitor has started charging. So let us consider a position which is corresponding to 1/3 VCC and 2/3 VCC, which we call it as VTL and VTH. Let this be, of course, 1/3 VCC. Let us call it as lower threshold voltage, and this is upper threshold voltage is this. So now this is VTL. Let me also have one more point which corresponds to VTH. So now as long as the voltage of your capacitor is less than VTL, so this voltage is, of course, this is less than this. So now the moment this exceeds this, when exceeds this, so now this is going greater than 1/3 VCC. When it is greater than 1/3 VCC, you know that V minus is more than V plus, so it is now 0. And of course, let us assume that this is also slightly greater than 1/3 VCC. So when it is slightly greater than 1/3 VCC, V minus is more than V plus, and here, here V minus is greater than V plus. So in both comparators, you will get 0, 0 output. When it is 0, 0, we know that flip-flop remains in the previous state. What is the previous state of your flip-flop? It is 1. So it continues to be 1 even when your capacitor voltage exceeds VTL. Now it is in VCC condition. Now the capacitors keep charging. When it is keep charging, assume that it exceeds VTH. Now this has gone above 2/3 VCC. So this has gone above 2/3 VCC. The moment when this goes above 2/3 VCC, this continues to be in 0 because this is compared with 1/3 VCC. The moment when this voltage goes above 2/3 VCC, so this will become 1. This will become 1. The moment when this becomes 1, it will go to reset. So this will become 0. This will become 1. Of course, the output has become 0 now. When does the output become 0? When the capacitor voltage exceeds 2/3 VCC. Now the output has become 0 now. The output has become 0. The capacitor which was charging through R1 plus R2. This was the path of your capacitor charging. So it was charging through, of course, time constant tau charge was R1 plus R2 into CT. That was your charging time period, time constant. It has charged here up to slightly greater than VTH. The moment it exceeds VTH, this becomes 1 and then this is 0. So now the output has become 0. The Q bar has become 1. So this is turned on. Once it is turned on, you can see here the capacitor now starts discharging through this path. So now it starts discharging. The moment it starts discharging, the voltage here will go slightly less than 2/3 VCC. The moment when the voltage at V plus goes less than 2/3 VCC, this will become 0. Of course, this is also less than, of course, that this is less than 2/3 VCC, but it is certainly greater than 1/3 VCC. So it is now 0, 0 condition. When it is 0, 0 condition, output remains in the previous state of 0. Now the capacitors keep discharging. So how your capacitor is discharging? The capacitor CT is discharging through R2. Now the tau discharge is R2 CT time constant. The time constant is now R2 CT because the capacitor is discharging through this R2 only. So now it is keep discharging. The moment when the capacitor voltage goes less than 1/3 VCC. When it goes less than 1/3 VCC, you can see here, when it goes less than 1/3 VCC, when it goes less than 1/3 VCC, which is more now, this becomes more. When this becomes more than this will make this as 1. S will become 1 and R is still remaining as 0. The moment it is S is 1, R is 0, the output again sets to 1. So Whenever the capacitor voltage just crosses 1/3 VCC, that is VTL, the output again goes to high. When it is high, this again goes to zero. When it goes to zero, there is no, of course, this will switch off. When it switch off, the current will not, or the capacitor will not discharge. Now it again starts charging. You can see it is now again charging. So when it again charging, this operation of going till VTH, and then once it reaches VTH, the output comes down. So once it goes to zero, the capacitor start discharging. Of course, it will go till VTL. So when it crosses VTL, the output again goes to high. This repeats. This repeats. So except the first cycle where it is starting from zero, from subsequent cycle, the capacitor will go from VTL to VTH, and then from VTH to VTL. This for the only for the first cycle. This for the only first cycle. So after first cycle, it will never go to zero. It will be slightly going less than VTL. By that time, the capacitor will, output will switch to high. Whenever the output switches to high, the capacitor, this switch goes off. When this switch goes off, capacitor cannot discharge any more less than VTL. So that's why the capacitor charging discharging voltage is VCT max is VTH, and minimum voltage is VTL. So that's what is a capacitor voltage. The output voltage is VCC and 0 volt. VCC and 0 volt. Okay, we need to understand, we need to find out what is this T off and T on time. T off and T on time. So for that, we have to use that capacitor equation of charging discharging and try to find out what is the expression for the on time and the off time. So let us have this circuit. Let us have this circuit and the waveforms. So we are supposed to find now. Of course, we already derived the expression for the on time and off time in terms of in case of your square wave generation using op amp. It is the same concept is used here. So let me now take the first cycle here. So let me take the stabilized waveform where the capacitor is already stabilized to VTL and VTH values. So this is this is T on, this is T off. Now this is my V0 waveform, and this is my capacitor waveform. So we see T, PC of T. So now we know that this is VTL. So this is VTH. So VTL, VTH in this case is 2/3 VCC, and so VTL and VTH. VTH is 2/3 VCC and VTL is 1/3 VCC. So we know the typical capacitor equation. VC of T is nothing but V final minus V initial e power minus T by RC. This is the typical RC time constant expression for the capacitor. For this particular circuit, for T is equal to T on. So what is V final? V final is the voltage which the capacitor may charge if T is infinity, which is equal to VCC now. Again, initial voltage for your on time is VTL and time is T on, and R, the resistance associated with the charging, is these two rays. So because the capacitor is charging through R1 plus R2, it is R1 plus R2, and of course the capacitor is C is equal to CT. And at this time of T is equal to T on, what's your capacitor voltage? So VC T on is VTH. So now what I'll do, I will do VTH is equal to VCC minus VTL into e power minus T on by R1 plus R2 into CT. Upon simplifying all those things, we can able to get the expression for T on as equal to uh, R1 plus R2 into ln of VCC minus VTL by VCC minus VTH. But this is a very simple mathematical substitutions you can do. If VTH is equal to 2 by 3 VCC and VTL is equal to 1/3 VCC, and if you substitute all those things, so this will become, oh sorry, it is CT is there. It is R1 plus R2 into C of T. This will become ln of 2. ln of 2. ln of 2, if you substitute and calculate, it is 0.693. It is 0.69 approximately. R1 plus R2 times CT. Similarly, replacing to find T off. Suppose if you take for timing T off, where the initial because this is your T off time, so initial value is VTL. The final value is 0, because finally if it is allowed to discharge, it will go up to 0, and the resistor associated with discharge is only R2. R1 is not coming to picture. Why R1 is not coming to picture is because when the capacitor is discharging, it just flows through this pin number 7. This is the resistor associated. It is R2 and capacitor is CT, and the capacitor voltage at T off. Capacitor voltage T off is this voltage. So this voltage is VTL. This is VTL. So this is VTL. Upon substituting all those things, you'll get the expression for T off as equal to R2 into CT ln of, it will be VCC divided by VCC, so it's not VCC, it will be VTH by VTL. So it will be as simple as this. So this is a fine, I'm just telling you the final expression. So it is VTH by VTL. So now this will be, of course, if you substitute VTH as 2/3 VCC and VTL as 1/3 VCC, this again comes out to be R2 CT as ln of 2. So it is 0.69 R2 CT is your T of time. So naturally, if you can see, T on is always better than T off, because you have R1 plus R2 here, it's only R2. So in this configuration of the circuit, T on is always greater than T off. Therefore, duty cycle is always greater than 50%. So if you want to get duty cycle less than 50%, then T on should be less than T off, which is not possible in this configuration. Let us see how do we do that to have duty cycle less than 50%. So before that, let us try to do an experiment on this stable multivibrator by having certain values of R1, R2. So I already rigged up a circuit using. Okay, let me run this. Okay, I'm already. This is my waveform. So you can see I'm already getting that square wave. Let me also show you the capacitor charging, discharging. Okay, this is perfect. Okay, let me just see. Let me tell you what are the values of R1, R2 that are connected for my circuit here. Let me just write a tabular column so that we can verify the values of R1. Okay, I'm having one of them as fixed. So now if I take the same circuit here, so R1 is connected as 3.3 kilo ohm, and R2 is a variable one. R2 is variable, and CT I have connected as maybe 0.1 microfarad. VCC is 5 volts. So R2, let me just keep it at different values. Maybe keep it 1 kilo ohm, then 10 kilo ohm, maybe you can make it 100k, maybe make it 100 ohm also once. Let us find out what is T on, what is T off, and you can also find what is the duty cycle, and you can find what is the frequency. So these are my practical values that I may get, because I just leave it to you to conduct experiment on different values of R1, R2, note what are the duty cycles and frequencies in different cases. I'm just giving a clue here. This is what I'm trying to do now. These are my okay. You can also observe the capacitor charging discharging voltages. Let me view. Okay, let me use this Y cursors, and let me have two normal cursors to measure what is the peak and VTH and VTL values. So this is VTH, VTL. If you carefully look at that, it's actually, you can see you are almost there. So this is 1.7, this is okay. Let me just make it few waveforms. Okay, let me make it okay. This is, I'm almost there. You can see now this is, so VTH, VTL is okay. This is what is 5 by 3 is actually 1.66, which you have it as 1.7. This is VTL. This corresponds to cursor 1. The cursor 2 corresponds to this VTH, which should be 3.33 volts. So you are having it as 3.37. So this is VTL and VTH values of the capacitor. Now let us also measure. Okay, let me just do the measurements also here. So what I'll do, let me measure define measurements channel 2. Okay, let me just, I'm interested in frequency. Okay, positive duty, positive width and negative width, and close. If you can see, it is certainly more than. Okay, let me just check what is the resistance that I have now. So now the resistance that is connected here is okay. Let me make R2 as 1K. Let me make this R2 as 1K now. If I make R2 as 1K, I have, okay, I can just change this time period to some smaller value. Okay, this is, okay, let me just do single run. You can see these are my pulse width. Okay, these are the values of the on time, off time, duty cycle. You can just verify these values. So let me write what is on time that is there here. It is 272 microsecond. The off time is 74 microsecond. The duty cycle is 78.5%. Let me just put its percentage here. The frequency is 2.88 kilohertz. So this is the values corresponding to R2 is equal to 1 kilohertz. Exactly this circuit. So this we are always considering it as 3.3 kilo ohm. Of course, here I have considered. This is for the first time it is made 1K. You see now the discharge is faster and charging is almost 3.3 plus 1K into CT. So naturally you can see the duty cycle is more because the charging resistance is 4.3K and discharge resistance is hardly 1K. So now let me make this as 10K. The moment when I make it at 10K here, let me see what happens. So this is just for now. Let me just uh, change this time to a bit more so that I can run. I can let me stop it. Let me just do it for maybe 200 microsecond. This is, or maybe 500, so that everything is visible. So now let me again run it again. Okay, these are my timings. So let me write it for 10K. So what are these values? So the on time is 836 microsecond. The off time is 618 microsecond. This is microsecond, and the duty cycle is reduced to 57.4%, and the frequency is 687 hertz. 687 hertz. Now this is for 10K. Let me make this 100K now. The moment when I make it 100K, again now always of course keep in mind that R1 is equal to 3.3K. Let me change the time division. Now this is, I think it's fine. Let me do single run. You can see now these are the time periods. So what is that you have on time as 7.3 millisecond, and this is 5.6 millisecond. Duty cycle is almost to 56.4%. The frequency is 76.5 hertz. You can see the duty cycle is always more than 50%, because you cannot make off time more than on time. So let me make this 100 ohm. Okay, when I make it 100 ohm, this is 100 ohm. I'll make all this as 0. Now this is 100 ohm. I'm just making my off time very less. Now the duty cycle should be too large. Let me see. Okay, because this time has, let me reduce the time to very small, maybe 100. Okay, this is fine. Or let me make it, okay, let me just, okay, this 100 ohm is too less. Okay, maybe we can just run it again, because it takes certain time to, okay, now this is fine. Okay, you can see this is, okay, let me just write the values here. So it is 213 microsecond is your on time. The off time is 9.1 microsecond. The duty cycle is 95.8%. The frequency is 4.4 kilohertz. These are the values that I have now. So now this is how we can able to get different frequencies, different duty cycle with different values of R1, R2. Here maybe for the experiment purpose, for my easiness, I didn't change R1 here. Maybe while doing the experiment you can change R1 also, of course CT also, but the intention here is to see the duty cycle can never be less than 50%. And of course this is how it is, keep changing. And of course capacitor voltage is going from VTL and VTH, which is 1.66, and VTH was 3.3 volt. So of course it was 1.71 volt. Okay, this is the expected, and we have slight variation, that's fine. Okay, now let us see the variations. So the variations that you can think of is, in this particular case it was said that it is this voltage of your pin number 5. You can see this is pin number 5 voltage, which is nothing but this point, which is nothing but this pin number 5 is this point. So instead of putting a capacitor here, to stabilize the voltage, what I can do is I can put a variable or I can put a reference voltage. I can put a reference voltage, or I can put an external battery to change the voltage. So I will make it as V external. So what I'll do, I'll take out this capacitor. So I'm sorry for that. I'll just simply connect something like this. I'll connect a battery. I'll connect a battery here, which is a variable one. So the moment when you not connected the battery, here it was 2/3 VCC. The moment when you connect an external battery, so this voltage which is 2/3 VCC will no more be 2/3 VCC. It will be the external voltage. It will be the external voltage. The voltage at this point will no more be 2/3 VCC. So what we are trying to do here is, so this was our pin number 5 point. So now what I'm doing, I'm not keeping that as 2/3 VCC. I want to connect a battery here. I want to connect an external power supply. I want to connect an external power supply. The moment when you connect the external power supply, this is no more 2/3 VCC. The voltage here will be V external. The voltage here will be V external. When you have V external voltage here, you have two resistors of same value. Then what will be this voltage? This voltage will also be not 1/3 VCC. This will be half of this. So this is now half of V external. So now this was VTH, this was VTL. Earlier VTH was 2/3 VCC, VTL was 1/3 VCC. Now the moment when you connect this external voltage source, the VTH will now become V external, and VTL will become half of V external. Suppose if you're connecting this as 4 volt, then VTH is 4, this is 2. The moment when you connect it as 2 volt, so then here it is 2 volt, here it is 1 volt. So I can able to change the voltage at pin number 5 from 2/3 VC to any voltage. So that's why pin number 5 is called as control voltage. You might have known that. What is the function of this? What is this pin called as? So this was actually called as control voltage. This is called as control voltage. Why it was called as control voltage is because I can able to control the voltage here. I can put a battery here and I can make this voltage any value. So you can able to change VTH VTL. So the moment when you change this VTH VTL, so naturally the on time off time will change. So that's why in this expression of T on T off, in this expression of T on T off, this is 0.69 R1 plus R2 into CT if VTH and VTL are 2/3 VCC and 1/3 VCC. See here. Okay, this is 0.69 R1 plus R2 into CFT provided VTH and VTL are 2/3 1/3. The moment when you are not having it as 2/3 VCC, this is not valid. This is not valid. So this equation changes to so when you're connecting an external power supply, so what is this C or T on? So T on is equal to R1 plus R2 into CT ln of VCC minus what is VTL? So VTL is half of V external. It is half of V external divided by VCC minus what is VTH? VTH is V external voltage. So this is the expression for your on time whenever you replace the control voltage by an external voltage. If you're not connecting anything over here, then it is 0.69 only. The moment when you connect some external voltage, the equation changes to this. How about the off time? You can see the off time you have this as the expression VTH and VTL. So what is VTH? It is V external, and what is VTL? It is half of V external. So if you solve for this, this will again become 2. So it is ln of 2 only. So off time will have the same expression whether you have external voltage or whether you have it as 2/3 VCC as the control voltage. So the off time remains constant whether you have an external voltage connected to pin number 5 or just leave it open. So T off is independent of the control voltage. That will just demonstrate. So what I'll do now here is, instead of connecting a capacitor here, so this was our circuit, no? Where was our circuit? Okay, this was my circuit. I will take out this capacitor and I'll connect it external battery and try to vary that. So that I'll do it in my analog discovery by connecting the power supply. Where is the power supply? I'll use this uh, one of my power supply which is there here as my control voltage. Okay, I'll come here. I'm using a wave generator. Okay, this is W1. I will use a DC of maybe any voltage. Okay, let me just make it as a basic one so that I can able to vary also. This is my some voltage. This is some. Okay, let me take this out and simultaneously show you people how does that voltage will change. Okay, now I have made this connection. Now there is a W1 connected of DC voltage to pin number 5. Let me just run it again for you all and then try to see what's the capacitor voltage. Capacitor voltage will be now swinging to this voltage. If I run now, if I run it now, you can see the capacitor voltage is now no more at 2/3 VCC, but it has changed to this voltage. So what will be this voltage? That will be equal to 2.18. What will be this voltage? This will be equal to half of 2.18, which is 1.09. That I'll show you now. So what I'll do, I'll bring this and then place it here, and I'll bring this and place it there. If you carefully notice that the voltages are okay, now this should be as per this, it is 2.18 is VTH and half of that is 1.09. Let me show you that. Do we have that value? I'll just make this here. Okay, this is for the timing is not that much important. Let me see what is the cursor. Can you see now it is 2.2, of course 2.28, which is the expected value which you are there here. So this is that this is my VTH value and this is VTL value. VTL value is almost half of that. So this is exactly because I didn't place the cursor properly. Now this is, so your VTH is now equal to your control voltage. So that is, control voltage is the voltage that is being supplied to a wave gen. So let me just show you that. Where is that? This one. You can. I'll just keep running it simultaneously. You see, the moment when I increase this control voltage. Okay, let me just take out this Y cursor also. Let me not include this. Let me just take out this Y cursor. Let me take out this also. I'm not interested in this now. Remove all. Okay, I'm deleting. Just have a look at how does this cursor, how does this VTL move. Can you see, is it moving up now? Okay, I'll just make this duty cycle a bit more. Just to make sure that, okay, where is that? Okay, just have a look at this is your VTH, which is now 3.33. I can see VTH has gone up to 3.85. So if you see here, is it not a large value? Can you see this is 4, this is almost 3.8, and this is half of that. So this is 1.9 something. So this is 2, this is 1.9. The moment when I make it equal to 2 volt, you can see I'll make it 2. I'll just run it here. Can you see the capacitor voltage, has it not reduced to 2, and is this VTL is half of that? Is this 2? Is this 1? Suppose if I make it okay, not 5, let me make it 4. Can you see VTH will become 4 and VTL become 2? Okay, this is not yet made 4. Let me make it 4 and then run. Why it's not happening? Oh, this numlock is there. Okay, 4. So now let me run it again. See now, has this not become 4? Is this not 4 and is this not 2? Of course, naturally corresponding to that your on time off time will change. So this is how you can able to make the control voltage to change VTH, VTL, VTH, VTL. So what is one more set of readings you can take here is over here in this set of readings. Maybe you can have for a certain value of maybe for R1, R2, certain values of R1, R2. Maybe this is 1K, this is 10K. Keep V reference as maybe 2 volt to 4 volt, 3 volt and 1.8 volt. Find out what is T on, T off, duty cycle, frequency, note the theoretical value, sorry, the practical values and find its theoretical counterpart. Theoretical counterpart, compare them. So that's how we can able to do the variation with the on time off time with control voltage. And let us see one more variation where you can able to change the duty cycle by bypassing the resistor R2. What I'll do is I will take a diode. I'll take a diode and bypass, because we know that on time was always more than off time, because while charging the it was always going through this. Now this was the thing. So while this capacitor was charging, it was passing through R1 as well as R2. Now what I'll do, I'll bypass R2. I will put a diode. I will put a diode such that when it is charging, it is going through the diode so that it bypasses. While discharging, it is still going through R2. So I will connect a diode in such a way that, so anode is going to number 7. Okay, here only I'll connect across this. So this is so now connecting. Okay, now I have connected a diode in this configuration. Now let me run now and try to see. Okay, let me just take out this control voltage for the time being. I will make the control voltage as 2/3 VCC only. So let me not use this. So I'm not using this. So let me just run this now. So now what I'm trying to do is I'm trying to get any duty cycle for that matter. So now my on time off time expressions will become, let me just show you that. What is the expression of so this was our T on T off expression. Where is this T on T off? This was our because when I'm just removed the control voltage, the T on was 0.69 R1 plus R2 CT, R2 into CT. So the moment when you put a diode bypassing this, so this is not there. So the equation now will become T on is equal to 0.69 R1 CT, T off is 0.69 R2 CT. So it's only R1, it's only R2. If you make R2 greater than R1, then T off is more than T on. So duty cycle is less than 50%. If R1 is greater than R2, then T on is greater than T off, then duty cycle is more than 50%. So I can get any duty cycle by having this configuration by making this R1 R2 comparatively more or less. So now let me do that. Since we already have R1 as 3.3K, let me make both of them as 3.3K and try to see what is the duty cycle. Duty cycle is almost to 50%. Let me take out this. Let me just have this. Let me measure. let me just only, okay, you already have this, so let me just say this. You can see it's almost white is 56% even though I kept 3.3k 3.3k, because while charging, you can just have a look at this. While charging, this small resistance of this is also included, so it's like, okay, 3.3k plus maybe 100 ohm, and while discharging it is 3.3k. So because of this small difference you have a small k, it's not exactly 50%. So what I can do is, uh, how do I get less than 50% duty cycle? Make this like 10k. When it is 10k, that is 3.3k. You can see what happens. I'm making R2 too much, so this is R2 10k. You can see now duty cycle is less than 50%. The one which we are okay, we could not get using without diode, we could able to get by using diode. You can see now the duty cycle is 30%. Even I can make the duty cycle 18%, even you can make it 20, or you can just make it as small as possible. Now what I've done here is the R2 is around 60k, whereas R1 is hardly 3.3k. So maybe let me just do it for some more time. You can able to see it. You can see it's hardly 7% because I have made the value of R2 as 60k and R1 is 3.3k. The other way is also possible. So what do you mean by other way? Let me make R1 very large, or let me make R2 small. So R2 I'm making it hardly 330 ohm or maybe 400 ohm. You can see now duty cycle will be very large. You can see now it is almost 89%, which is pretty large. So using a diode, you can able to achieve, using a diode to bypass R2, you can able to achieve duty cycles of any percentage, from 10% up to 90% or even 95% you can achieve. So this is what is the different configuration of your Astable multimeter. So first what we did, we configured only this circuit with control with capacitor CS connected between 5 and ground, and we removed this capacitor because we connected the external voltage and then we try to vary that voltage, and the expression for your on time will differ from uh, this 0.69 R1 plus RT to this value. And we also bypass, of course, in the previous case off time remains the same even with external or without external. And to get duty cycle less than 50%, we connected, or any duty cycle we connected a diode bypassing this resistor R2, so you can able to get any waveform. Okay, that will give you a confidence on using 555 timer to generate square wave of any duty cycle. And how does this maybe I can also show you the possibility of generating a PWM waveform using this control voltage. So what I'll do now here is I will use this, I'll use maybe let me use a bit high frequency. Okay, let me make this 3.3k. Okay, almost. Okay, let me try to get, this is okay. Let me run this and try to see what is the duty cycle that I'm getting. It's almost 50%. So now with this 50% duty cycle to 2 kilohertz, let me apply a sine wave of frequency 100 hertz, of frequency, this is 100 hertz signal, of amplitude maybe just 1 volt, with an offset of Okay, maybe let us make it as 2.5. Let me also have an amplitude of 2 volts here. If you see what happens to this now, you can see look at a pulse width modulated waveform. I'll take out this. I will show you that pin number. Use this here. Let me show you that sine wave and okay. Let me change this time period to okay. Let me make it. Let me just put them bit aside. Let me offset. Let me make a sort of minus, maybe minus 5 watt is better. This is interesting to see. See now I'm applying a control voltage which is a sine wave lighting. So when the control voltage is less, you have lesser on time. Okay, lesser on time. You can see the on time is less. On time is least when it is at the positive peak, sorry, negative peak. When it is at the positive peak, the on time is maximum. So this what we call it as pulse width modulated waveform. The width of the pulse is changing according to the control voltage. If the control voltage is more, then width of your on time is more. You can see when the control voltage is less and less, the width of your on time is keep reducing. So the on time depends on the control voltage. If the control voltage is sine wave of certain amplitude, then naturally the width of your output waveform, especially the positive width of the output waveform changes. So this is what we call it as pulse width modulated waveform. That is PWM. PWM, that is pulse width modulated. So let me show you that. This is pulse width modulated signal waveform. This is PWM waveform pulse width. So this is usually used for controlling the speed of the motors. So to do that, so what I did here is uh, I used a signal generator of frequency 100 Hz with an offset of 2.5 and with an amplitude of 2 volt. I'm applying it to pin number 5. Let the frequency be less so that you at least have few tens of at least 10 or 15 cycles of your square wave within this. You can see this is my cycle. In this cycle I have a certain number of pulses. So this will end up in getting a pulse width modulated waveform. So these are a few variations that you are supposed to do it in square wave generation. One is without any control voltage, what is on time off time duty cycle. Duty cycle is always more than 50%. Then you apply control voltage, see what is VTH, VTL, is it equal to external voltage and half of external voltage. That is second variation. The third variation is connect a diode bypassing what resistor R2, that is discharging resistor during charging time. Again repeat that. And the last one is you apply a sine wave at control voltage with DC offset, and you see this pulse width modulated waveform. Pulse width modulated waveform, and of course you can measure what is this time, the maximum time, and what is the minimum of time. That's it. Have a nice lab.